Swayam Prabha. Digital India. Educated India.
Students, so we have started discussing on three-phase equilibria in ternary system, and I just told you that the three-phase equilibria consisting of alpha, beta and liquid can be represented by a ternary triangle. I hope you remember that I discussed with you about ternary triangles, and this basically is a triangle connecting three phases, and I have given you a brief outline of what is that. So, before that, let me just tell you that how a ternary triangle looks like. Well, this is the Gibbs triangle ABC. Suppose we have a phase, we have a alloy composition given by point P here, and after some transformation from liquid to solid or solid to solid, it forms three phases given by SRL. So, the points on the Gibbs triangle connecting the compositions of these three phases SRL is basically represented by a Gibbs triangle, and this can be used to measure volume fraction of the phases. I am not going to go up details of that. The bottom construction here is showing the same thing, that how the phases can be determined easily. As you see that the different lines can be done, and one can determine the percentage of phases. This has been integrated in the slide, and I have discussed you in the class also. So, well, there are as you know, there are in a ternary system, let me just go back. In a ternary system, there are actually three components. So, degrees of freedom F is given by C minus P plus 1. So, there are three components, and we are discussing about three phases. So, degrees of freedom is 1. So, when there are three phases, there are 6 independent composition variables, right? Why? You have suppose liquid alpha, beta as a three phases. The compositions of liquid are represented by three elements: XA, L, XP, L, XC, L, right. Similarly, for alpha also XA alpha, XP alpha, XC alpha, and beta also XA beta, XP beta, XC beta. And we know that XA plus XP plus XC equal to 1 for a particular phase, liquid alpha or beta. So, therefore, we have 6 independent composition variables. The last one is automatically determined by the relationship I told you, XA plus XP plus XC equal to 1, correct. So, for liquid is XA L plus XP L plus XC L equal to 1. So, if I know 2 of the variables known, then third one is automatically determined. In addition to that, you have a temperature as a variables. There are 7 independent variables, right. So, out of the 7 independent variables, one of the degrees of freedom is 1, correct. So, that means that we can vary one of the variables, others cannot be varied at all the other variables according to Gibbs phase rule. Now, there are different types of three phase equilibria exist. What are these three phase equilibria exist? One is obviously liquid going to eutectic alpha plus beta. Second one is, this is the eutectic. Second one is a peritectic, liquid plus alpha going to beta is called peritectic. Third one is liquid L1 plus L2 going to alpha, this is syntactic, and another one liquid going to alpha plus L2 this is monotectic, and finally, you have two solid state reaction, eutectoid and peritectoid. Okay. So many 3-phase equilibria are possible, 6 actually, but it is not possible for me to discuss each of these 3-phase equilibria, in terms of the ternary phase diagrams. So, I am going to show you some of these 3-phase equilibria in a ternary space model, but I am going to concentrate on a particular 3-phase equilibria which is more common and discuss further about that. So, what are these diagrams? Okay, let me tell you. Suppose you have the first one which is shown here slide. You can have out of the 3 binaries, okay, there are 3 binaries. Suppose this is one binary AC, okay. This binary has isomorphous themselves, correct. Then you have another binary BC that is also isomorphous phase diagram between themselves, and third binary which I am not drawing has an eutectic reaction, liquid going to alpha plus beta. This will lead to 3-phase equilibria between liquid plus alpha plus beta, correct. And as I told you, the 3-phase equilibrium can be represented by a tie triangle, that is what is shown here, liquid plus alpha plus beta. We will discuss more about that in later. So, this is the first type of 3-phase equilibrium system we can discuss. You have, please remember that the first ternary phase diagram I discussed with you in detail is basically isomorphous system, in which all the binaries between A and B, B and C and C and A form are basically isomorphous type of phase diagrams. So, the ternary phase diagram is also isomorphous. Here, because one of the binaries shows a eutectic phase diagram, the equilibrium condition gets equilibrium situation gets changed. It becomes 3-phase equilibrium. No longer we have 2-phase equilibrium existing in the ternary system. We can also have a situation in which one of the binaries, like here AB, you can see, is basically isomorphous type, but other 2 binaries are eutectic type. You can clearly see here eutectic. Third one I am not drawing, and then we also have a 3-phase equilibrium at the center. The third one, so first one was two binaries were isomorphous, one eutectic, second one was 2 binaries were eutectic, one was isomorphous. Third one is that 2 binaries will have isomorphous systems, but one binary will have peritectic. You can clearly see 2 binaries AC and BC has a isomorphous, but on the other hand binary between A and B has a peritectic reaction. What is that peritectic reaction? Liquid plus alpha going to beta, correct. So, this is the third situation. Finally, fourth one, you can have 2 binaries as a isomorphous and one binary as a monotectic system, correct. So, out of the 6 I am showing only to you 4 different types, or rather 3 different types, or 4 actually, not 3. Isomorphous plus eutectic, isomorphous plus peritectic, isomorphous plus monotectic. So, that means what? We can generate this 3-phase equilibrium, or we can have the 3-phase equilibrium under different reaction conditions, and that makes us that the chapter on these will be a very long chapter. If one has to discuss every situation in the text in the lecture, then it will take long time. So, we cannot do that. So, what we will do? We will take a system which is more generic, that is a system which has one of the binaries as isomorphous type, other two binaries as eutectic types, correct. So, let me just go to the board and tell you how it will look like. So, suppose this is my Gibbs triangle. So, this is one binary, this is the another binary, and this is the third binary, correct. As I said, one of the binaries will have isomorphous, other two binaries will have eutectic. So, this is about this second one, third one will be also eutectic. So, this is what is the situation. We want to discuss, and as I told you, this is a very generic situation, that is why we will discuss in detail. So, what all we will discuss here? So, this is the three binary phase diagrams. We need to develop the ternary here and then go ahead different aspects of the ternary phase diagrams. So, first thing we will discuss is a 3D model, 3D space model, that will tell us how this phase diagram will look like. Second thing we have to discuss is the different shapes of different regions, shapes of single phase, two phase and three phase regions. Third thing we will discuss about isothermal sections. Fourth is vertical section, and fifth is the solidification behavior. So, we are going to do one by one, but first thing I like to impress you upon is that there are phase diagrams which follow such a kind of things like bismuth, antimony and lead. Between lead and bismuth and lead and antimony, lead and bismuth, lead and antimony, you have a eutectic phase diagrams, but bismuth and antimony forms isomorphous. So, ternary phase diagram will be what I am going to discuss, will have lot of similarities with these phase diagrams. So, there are many such examples. So, now how this space model. Well, before I do that, so this slide tell you this is the one with two isomorphous, one eutectic, two eutectics, one isomorphous, one peritectic, two isomorphous, two isomorphous, one monotectic systems. So, let us now discuss about the Ternary space model of the system which I have been telling you. Okay. So, I will just draw it to keep it things nicer. I am going to draw it from this chart what I have drawn myself. So, let me just draw it on the right side, so that you understand it nicely, the 3D space model. So, first I have to draw little bit, I have to distort this triangle to show you the 3-dimensional projection, otherwise you cannot see it. Okay. So, first is that between A and C you have isomorphous system. You can see here between A and C there is isomorphous system. So, this is T A suppose. So, this is T C. Now, between B and C there is an eutectic. So, this is the eutectic, and this eutectic will mark as E2, and then between A and B there is eutectic. Please follow the way I am drawing it, so that you can understand it nicely. This little bit. Okay, so this is my E1. So, now I remove other parts. As you see here, this is the ternary space model of the phase diagram. Okay. So, now one can actually put different numbers. This is suppose C1, this is D1, this is A1, this is B1, okay. And similarly this is A2, B2, C2, D2, correct. So, we will connect these 2 points. Why you are connecting? One thing you have probably seen that I have kept alpha, alpha, alpha same, correct. You could see here the alpha phase between A and C is same as the alpha phase between B and C. They are sharing the coordinates. Similarly, alpha phase here also sharing the coordinates with the C. Beta is sharing the coordinates. That is why we can join this point. This is actually alpha zone. Similarly, we can join these 2 points. This is my beta zone. Okay. Now, one thing you have to understand here, because you have eutectics here. So, you need to know where these eutectic lines in the ternary goes, correct. So, let us connect these. And we can write down x, y, z. So, basically the point I am trying to make is that ternary equilibrium between alpha, okay, I have not marked the phases here, otherwise it will be complex, between alpha, beta and liquid has a triangular shape, and this is the tie triangle which we are discussing, which we are going to do much more in the next series. Okay. So, this is TB. I hope this you can draw yourself. initially when you start drawing it might be looking little bit complex, but you should try drawing yourself. So, we have generated the ternary phase diagram from these binaries basically as you see here. So, now let us go to the slides, because slides are more important. Let us go to slides and discuss. So, as you see here, these are the liquid surfaces, these two, and solid surfaces are also shown here, and this is alpha, this is beta, this is alpha plus beta. What does it mean? Basically, at temperatures lower than the utility temperatures E2, you have alpha, alpha plus beta and beta 3 phase fields in the bottom. It will be clear, much clearer when we discuss this. Now, upon discussing this 3D space model, okay, which is again shown here, let me discuss about the shapes of the different zones, different things. So, what we have here basically, there is one 3 phase region, alpha plus beta plus liquid, and there are two 2 phase zones, alpha plus beta, beta plus liquid and alpha plus liquid. Okay. So, let me write down. So, you have one 3 phase region which is alpha plus beta plus liquid, and you have two 3 phase two phase region, three 2 phase region. What are they? Alpha plus liquid, beta plus liquid and alpha plus beta, right, and there are 3 single phase. Region. What are they? Alpha, beta and liquid. So, we need to see each of these shapes of these things. Okay. At least we need to see alpha, beta, alpha plus liquid, alpha plus beta plus liquid. Then it will be clear to you how the things looks like. So, now again the 3D space model is shown on the right side. As you see here, 3D space model is shown on the right side. What do you see here? You see that the triangle which is shown as here, liquid plus alpha plus beta, is what is known as the 3 phase equilibrium zone, and it's basically remain same. Here also at the bottom also will show it will remain the same. Wherever till the temperature at which this 3 phase equilibrium exists, you will have the same things. So, that is let us now see what is the alpha looks like. Alpha looks like this trapezoid, you can see here. I have drawn in the last class also. This is the one. I do not want to draw it on the board because this will consume lot of time. So, this is what is that, and then you have a signature of these isomorphous at the top, and this is my alpha. Correct, clear? You should try to draw and see that. So, beta will be smaller than that. You can see here, this is beta, this is like this is like this. Correct, this is the beta. So, these two are my alpha beta zones. Then what about the alpha plus liquid? Alpha plus liquid is this zone, you see here. Although it looks like from the perspective it looks like this kind of stuff like this, but it is not. Okay. Anyhow, so the way it looks like is this is what I had drawn it just now, and then you have this zone, correct. It is quite complex. On the other hand, liquid plus beta is much simple. It is like a pyramid, but angular. These are all known as ruled surfaces. Why? Because you can draw the tie lines. You can see here the tie lines are dotted lines, tie lines, so on. You can join the liquid 2 phase zones with the tie lines because it is liquid plus solid. Similarly, here also you can join the 2 phase zone with the tie lines, correct. So, that is how this shapes, and alpha plus beta is very easy. You can see here how does it looks like. It is just like that. is shown very clearly. This is this part, and that part, downward part, is also shown, correct, and then the top one is shown like this, but at the bottom you see there is a triangle remain. So, this triangle is alpha plus beta triangle. On the other hand, the most important zone which I have shown you our last class is the liquid plus alpha plus beta. That looks like this. Okay. Basically, it looks like a triangle. You can see, no, this is a triangle. Okay. Now, as you know, vertices of each of this triangle is basically telling you the compositions of liquid and alpha and beta, and as the temperature goes down, the compositions also do get changed, and because of that, what you generate basically is a series of triangles, and these triangles we can actually draw tie lines also. These are the triangles. Okay. Each of these triangles are shown here, and one can actually draw these tie lines inside that. Okay, let me just go back to this picture. You can see here, these are the tie lines. Okay, we have drawn, right. These are initially it is difficult to grasp or understand, but once you have a feeling of this three-dimensional space, you can actually realize it that this looks like that. There is nothing more than that I can do other than showing you the picture and drawing it on the board, but you have to yourself have to practice it. So, these are the triangles, and you have a this end you have binary eutectic, also this end you have binary eutectic, they are joined, correct, and this is the tie lines between alpha plus beta or liquid plus beta. Okay. So, these dotted ones are between alpha plus beta, and these solid ones are between liquid plus beta, and this one is alpha plus beta liquid. Okay. There are three different colors are shown. So, this one I am showing you is basically liquid plus alpha, this one which is blue color is basically liquid plus beta, and this is alpha plus beta. So, therefore, I have shown you all the three zones, and now actually I am going to discuss about the vertical sections and the certifications of these other things in the next class, because this is this requires further discussion. So, of the space model, but anyway every time I am going to discuss with the space model. So, you should better concentrate on the space model carefully. Particle section, isomer sections we will discuss today.